Welcome, everyone. Just wanted to say thank you for being here today. I'm Gina Henry. I'm the Associate Dean for Advancement in the College of Engineering. In the summer of 2020, the College of Engineering kicked off a new webinar series called Faculty Insights, a 20-minute briefing. We've hosted about 5 per year since the inception of this program, and we're looking forward to more future programs as well. In this virtual series, faculty from across the College of Engineering share insights into their research, its impact, and they provide perspective for the future. Following each of these 20-minute presentations, the attendees have an opportunity to interact directly with the speaker and direct questions and comments to our speaker. If you've been on any of these Faculty Insights sessions before, you'll see that today we're going to stray very slightly from the standard format because we're joined by a very special guest, and that is John Kagan, who is the David and Susan Coulter Head and George Talman and Florence Barrett Ladd Professor, and also our recently appointed Head of Mechanical Engineering Department. John joined the College of Engineering in 1990 as an assistant professor, and his career spans collaborative and innovative work in education, research, and industry. Researching engineering design, automation, and methods, John merges AI, machine learning, and optimization methods with cognitive science problem solving. He exemplifies the College of Engineering's culture of advanced collaboration, having worked with engineers, psychologists, neuroscientists, marketers, designers, computer scientists, and architects, just to name a few, in his work. He also co-founded and co-directed the Integrated Innovation Institute. In addition, throughout his tenure at CMU, John has been called upon to serve in a variety of leadership roles, including Interim Dean, Associate Dean for Graduate and Faculty Affairs, and Chief Academic Officer of the College of Engineering. He was recently honored with the Robert A. Doherty Award for Sustained Contributions to Excellence in Education and the College of Engineering Outstanding Service Award. He's active in professional societies and boards and is a fellow of the American Society of Mechanical Engineers, and was awarded the ASME Design Theory and Methodology, Design Automation, and Ruth and Joel Spira Outstanding Educator Awards. John has authored several books, more than 300 publications, and is an inventor on multiple patents. We are absolutely thrilled to have him serving as the head of mechanical engineering at CMU. I'd like to ask John to say a few words before we begin Carmel Majidi's presentation this afternoon. But before I turn things over to John and Carmel, this is just a reminder to please submit any questions that you might have for our speakers via the Q&A feature at the bottom of your screen. You should see a little Q&A button at the bottom. And I'll be back to help with the Q&A session, and our speakers will respond at the end of the presentation. But you can submit a question at any point during the presentation, and it'll show up in the Q&A feature. So with that, I would like to turn things over to John.
Thank you, Gina. Very kind introduction. It's so great to, well, I would like to say great to see you all, but at least to be with all of you. And thank you for your time and for being here. I'm going to tell you just a couple of minutes to tell you a little bit about mechanical engineering in the college, and then really excited about introducing Carmel Majidi to you. It's a really exciting time, certainly in the College of Engineering, and most particularly in mechanical engineering. We will be opening our brand new home, Scaife Hall. It's a new Scaife Hall. It's going to be 85,000 square feet of space for learning and for research and for students and for people to congregate. And we'll be moving there into this new building come summertime, the end of April. We can start to move in. So we're quite excited about that. In the building, there will be a focus on learning. There'll be multiple types of classrooms, very much current classrooms, student lounges and meeting areas for students, as well as a lot of focus on research. We look at mechanical engineering at Carnegie Mellon as a forward-looking mechanical engineering department. I like to say, if you think about gears and springs, when we look at gears and springs, they're at the nano level. So the labs in Scaife Hall will include focus on robotics, brain interfaces, nanotechnologies, such as being able to create structures out of DNA, and soft robotics and soft botics, such as the work you're going to hear about today. We also really like to think about learning across the curriculum, learning by making across the curriculum. And that's for mechanical engineering, but for the entire college. And many of you may be familiar with TechSpark, which of course is our really state-of-the-art, probably one of the best maker spaces, machine shops, et cetera, in any university, I think, in the country. And we also like to think about learning through research. Many of our undergraduate students, both in mechanical engineering and across the college, are very much engaged with research. Just real quickly, I think you probably are familiar, but if not, our college is very well ranked. We're 4th in graduate and 6th undergraduate, and mechanical engineering is also in the top 10 at 10th graduate and 9th undergraduate rankings for the US News and World Report. Mechanical engineering has about 900 students, half graduate, half undergraduate, with 40 faculty. And we're actually quite proud that more than a quarter of our faculty are women. So we are really focused on trying to make this a diverse, equitable, inclusive environment for all. And with that, I actually am very excited to join you in watching today's speaker, which is Professor Carmel Majidi. Professor Majidi is the Clarence H. Adamson Professor in Mechanical Engineering and the director of the Soft Machines Laboratory that integrates soft materials for human-compatible machines and electronics. His current research focuses on elastomer composites that and soft microfluidic systems that exhibit unique combinations from a mechanical, electrical, and thermal point of view, and can function as artificial skin, nervous tissue, muscle for robotics and wearables. And we'll hear about some of that in just a moment. Professor Majidi received his PhD from the University of California at Berkeley and joined Carnegie Mellon in 2011 after having postdocs at Harvard and Princeton. He also has 3 current spinouts from Carnegie Mellon from his research. And so it's a really great example of his ability to create fundamental academic foundations and bring them to practice alike. I would say he's one of our superstars. He's also a really great person as well. His title today of his seminar or talk with us will be on soft robotics, building robots for everyday life. Please welcome Carmel Majidi.
Thank you so much, John. Thanks for the very kind words. I must say it's a tremendous pleasure and honor also to have John Kagan as department head. He's been inspiration to me and a lot of the faculty here. Has done really kind of pioneering work and done tremendous work kind of in not just in academia but also kind of in innovation and in kind of other domains. And so having him at the leadership in the department is going to be amazing for us, tremendous for us as we kind of move into this next era. So thank you so much. So let me do share screen here and I'll get started with my presentation. I want to just start by saying that the presentation here is going to cover soft robotics at a fairly high level. So if I can get control of my, there we go. Cover at a fairly high level, and I'll kind of sprinkle throughout some of the work out of my research group. But at this point, soft robotics and what we kind of term soft botics here is really a global initiative, and CMU is one of the leaders and a lot of the pioneering work, even since the inception of a lot of the kind of the current efforts in soft robotics happened here at CMU. And so talk about kind of how some of the work out of CMU kind of weaves into this. And then John mentioned the new SCAFE building, and so at the end also I'll talk about how central that's going to be for really accelerating a lot of the work that we do in this domain. So, I mean, soft botics, soft robotics, of course, robotics, as we know, has a central role in a lot of different industries in our economy. They're absolutely critical, vital for a lot of what we do. A lot of these machines, these robot arms that you can see here, are highly well engineered for the tasks that they're designed to accomplish. Now, of course, as you can tell here, these are pretty bulky, load-bearing, powerful systems. Oftentimes they work behind cages. You certainly don't want these in close proximity to humans. You definitely don't want these, say, robot arms in your kitchen, right? these are really not designed for interactions with humans in a kind of a close proximity role or an assistive role. And really that's where soft robotics and this kind of concept of soft robotics comes in. Can we re-engineer machines and robotics that are used in automation in a way that they can actually be more engaged in our daily life? So engineer them in ways that they can assist with mobility, that they can aid with human computer or human machine interaction. We can use these for healthcare, for health monitoring. And what we find is when we explore kind of the role of robotics for applications that require intimate contact with the human body, we're faced with a lot of challenges in the materials domain. So when we think about robotics, we think about a lot of different disciplines, I mean, not just the hardware, but also the AI and the computer vision and kind of the more algorithmic sides of robotic systems. But there's also a lot of materials challenges that also emerge when we start to think about interfacing these automated systems with the human body. And in particular, we want to think about next generation material systems that basically function like artificial sensing skin or artificial muscle or kind of artificial nervous tissue for embodying intelligence within these systems. Now, of course, the big challenge is that existing materials that are used in engineering don't have any of these functionalities. They're for the most part passive from an actuation type standpoint. They can be load bearing, or can use them in garments, and they can kind of provide comfort and protection. But if we want to engineer any kind of electronic functionality, any kind of robotic or actuator type functionality, then we do end up with systems that are quite bulky and at the end of the day, really not compatible with just our everyday life. I mean, if you think about everything from mobility to wearable electronics, like you can see here in the bottom middle panel, these are devices that would interfere with our ability just to kind of do day-to-day tasks. And so this introduces kind of a new paradigm in engineering, which I call soft matter engineering. And this is actually something that in kind of the earlier days of soft robotics, I was kind of advocating as kind of an important pillar of this field. And that is to really kind of rethink the types of materials that we use in engineered systems. And one way to think about materials and their compatibility with the human body and the compatibility with our kind of natural day-to-day activities is to think about how stiff these materials are. How much force does it take to stretch these materials? Or alternatively, as we say, put these materials in our clothing, or we put them in robots and machines that we interact with, how much force do they kind of push back with when we do come in contact? And the reality is that most engineered systems, the types of materials that are used are orders of magnitude stiffer than the soft, squishy materials that make up our body. And that's what makes a lot of automated robotic systems quite dangerous for physical contact with humans. This vast mismatch in the stiffness between the hard plastics and the metals and the semiconductors and all the kind of the hard case packaging that goes into kind of conventional hardware versus kind of the soft squishy tissue that make up our body. And so really the goal here is to really carefully re-examine the types of materials that we use to engineer systems and see if we can actually achieve a lot of the same robotic and computing and electronic functionalities that we historically achieved using rigid materials, but instead using soft materials, rubbers, gels, granular material, kind of like, things like sand or powders or fluids. So, I say kind of a lot of the early, pioneering work in soft robotics actually started out here at CMU. However, if you, really want to, make a stretch, I mean, you could actually kind of argue that the inception of robotics goes back many decades, back to the 1940s and 1950s, with a lot of the early work using pneumatics in automation and robotics. So, there's a really long history here of just using basically balloon inflation and using kind of pneumatic power to create these fairly simple and somewhat rudimentary linear actuators that have been used for applications. Kind of go into this a little bit later, but robot arms and and also in kind of industrial automation with, say, conveyor belts and hoppers, but also, as you can see here on the far left, using these kind of soft pneumatic robots for a hand exoskeleton. This is actually Joe McKibben, a physicist who's kind of credited as being one of the pioneers of soft robotics. He built this hand exoskeleton using pneumatic actuators for his daughter, who was suffering from motor disabilities. In the decades since, I mean, there's been kind of expanded look at these different types of pneumatic actuators for different applications, mobile robotics, again, robot arms, industrial automation, looking at different types of form factors, shrinking these down. Within the past, 2 decades, we've seen tremendous growth in institutional funding for soft robotics, and basically almost a rediscovery of these types of soft material systems for applications in robotics. So that kind of leads us to kind of where the field is today. There's all sorts of really exciting approaches and designs to building machines and robots that don't use any motors. They don't use any of the conventional kind of hardware that we typically associate with kind of motorized systems and automation. Instead, they use all of these kind of alternatives to motorized actuation. So pneumatics, of course, is one, but there's a host of other types of actuator technologies out there. So really quickly, I'm just going to kind of go through these. It's going to be rather rapid, but just I want to give you an overall flavor about kind of what the current state of the field is and the types of different methods that are used to kind of power these systems so that they can have robot functionality, but still be made primarily out of soft and squishy materials, so they can be safe for contact with a human and also kind of mimic the properties of soft natural organisms. So I'll start with shape memory alloy. That's been a really popular material in soft robotics. And so some of you might already be familiar with materials like nickel titanium that have this shape memory effect. At room temperature, they're quite compliant, quite deformable. But then when you heat them up, they basically spontaneously will go back to their original shape. And so you kind of see this in the video here on the left. It's very malleable. You can deform it, uncoil it. And then when you bring a flame to it and it heats up, just magically, the material had memorized its kind of previous crystal structure and then will spontaneously go back to that shape upon heating. So you can see that here now the wire remembered that it was a coil and it's going to go back to that shape. Now, heating is, of course, one way to do this. I mean, here's us kind of showing the same effect in a hot water bath. But the approach that we take in our group and other groups throughout the world is, instead of using external heat, to use electrical input. So we basically pass electrical current through that shape memory alloy, and then through the Joule heating, basically the resistive heating that we get from that current flowing through the wire, basically that's enough to create the temperature needed to induce these this shape memory effect. And these are real-time videos. We can get somewhat lifelike motion. Let me play this video here. This is a brittle star-inspired soft robot that's kind of crawling towards this target here, and I'll kind of skip ahead as we move this ping pong ball. You can see that the robot senses that the ping pong ball has moved, and now it's changing course to follow it. This is all accomplished using these shape memory alloy artificial muscle actuators. So we're not using any of the conventional motors that we've traditionally seen in robotics. Another kind of really popular and exciting approach to actuation is to use biohybrid type systems. So actually taking natural muscle tissue and combining that with soft materials to get robot motion. Adam Feinberg over in the BME department has been one of the pioneers in these kind of soft biohybrid type systems, combining natural tissue, in this case skeletal muscle from mice or cardiac myocytes and basically cardiac tissue from a rat's heart, and then incorporating that into soft material systems to get these robots to move. So I'll just kind of breeze right through. We'll have time during Q&A to kind of come back if you want to learn more about some of the details of these. I really want to highlight some of the applications of these material systems. like I said, one of the pioneers of soft robotics was a physicist, Joe McKibben, and what motivated him was to make this hand exoskeleton for his daughter. And that continues to be a motivation for the field. This is work out of Harvard University, actually, Connor Walsh, using these kind of soft pneumatic actuators to assist in hand motion and this is really intended for rehabilitation and assistance for patients who suffer from motor disabilities. Here's I'll step back here, another video of using soft robotics for a medical endoscope. So minimally invasive surgery is another big motivation for soft robotics. Because again, these materials are soft and deformable, we can put them through arteries, we can have them in contact with organs without having to worry about these high stress concentrations that might arise from mismatches between the stiffnesses of the contacting material. So by using materials that match the stiffness of our natural arterial tissue and our organs, we can reduce those stress concentrations and ensure a safer contact. And so these systems are still very much work in progress. I'm not aware of any actual surgical operations that are routinely being performed using soft robotics. Although there's every year millions of balloon angioplasty operations, and you could argue that those, in a sense, are kind of a form of soft robotics because they also use inflation and soft materials. In that case, to basically remove any plaque from arteries. Here's another example of a popular area of research exploring kind of the use of soft robotics in medicine. This is work by Metin City, who is a former member of the MechE department here at CMU. He's now at the Max Planck Institute, and he, along with plenty of others, have explored the use of soft magnets to create these little robots that can kind of crawl around and move inside the human body. What's special here is that we basically get this kind of untethered type of interaction between these external electromagnets that are outside of the body, and then these kind of soft, kind of rubbery magnets that can be kind of placed in, say, in the stomach or in different, again, in the arteries or in different organs. This is just, I think, one of the last application demos here. This is work out of Stanford University using soft robotics for haptic interfaces. And this is something also that we're doing quite a bit of here at CMU. I think this represents kind of one of the important application domains where soft robotics does offer some unique advantages over a lot of kind of more conventional hard-cased electronic technologies. Here, we're using kind of pneumatic inflation, or I should say we're using pneumatics not just for creating shape change to create these different textures and surfaces for haptic feedback, but we can also use pneumatics for stiffness tuning. So if we put particles within these kind of rubbery chambers, and if we, say, apply suction, then that can actually cause those particles to kind of compact in. And that's a way of achieving stiffness. And then this is just wrapping up to some work out of my lab where we're incorporating soft sensors into these robot grippers. Again, this one is powered using shape memory alloy. And by using these kind of soft sensors and soft electronics, we can endow these soft robotic end effectors with this feeling of basically touch and a sense of proprioception, or a sense of motion and orientation. So the types of electronics we use here are based on liquid metal. So instead of using just conventional copper or gold traces, we're using metal alloys that are liquid at room temperature. And so this allows for kind of fluidic circuits that can conduct electricity, that can themselves function like sensors, so in this case, touch sensors, but then we can also wire up different microelectronic chips like an IMU for measuring motion. We have a little light-based time of flight sensor to scan the location of objects. And by incorporating sensing into these soft robots, we can basically make them much more robust. And so when we introduce disturbances, if we say move an object around, or if we try to pull it from the grips, the sensors will pick that up and the robot will know to go and reattempt the grasp. And naturally, a lot of these kind of soft and stretchable sensors and electronics are not just useful for applications and robot grasping. Here's just another video of work. This is in collaboration with Lin Yao's group over in the HCI Institute, where together we looked at using a lot of the same material architectures and manufacturing methods used in soft robotics now to create these kind of sticker-like sensing electronics. And I'll just kind of skip ahead here. That can be used to basically create these kind of fully wireless circuits that we just adhere to the body, and we can use for all sorts of different modes of physiological sensing. So here's just an example of a sticker. It has its batteries, it has its microcontroller, it has a Bluetooth radio, and then it has IMUs, so we can track, say, the motion of the knee. The electronics themselves are quite robust, quite stretchable, so we can put them into garments, we can put them on our skin, we can move around, and they don't really kind of interfere with our natural motion. The electronics will stay intact. And we can incorporate acoustic sensors. If you want to, say, track food intake, we can put temperature sensors, pulse oximetry chips. I mean, there's a whole range of different types of sensing modalities that we can engineer into these. So I have about 5 minutes left, and I'm going to spend a little bit of time just talking about the impact of this field and also kind of translation into the commercial and entrepreneurial space. And John, in the introduction, he kindly mentioned just some of the translational work that my own group is doing. So I wanted to end by talking about some of the stuff that we're doing with commercializing some of the technologies that we're developing here at CMU. So certainly from an academic standpoint, there's been tremendous growth in the field. If we just look at the number of research publications a year, that's been growing almost exponentially. And it really has picked up over this past decade. Once when a lot of institutional funding agencies like the National Science Foundation, like DARPA, stepped in and started really focusing on this as an emerging field. And we can also look at international conferences and also the emergence of journals that are focused on this theme of soft robotics. So it's been an incredibly productive and successful time period for a lot of faculty. But I would say, more important, it's also created tremendous opportunities for companies. So both established companies as well as startups and including CMU spinoffs that have found ways of harnessing a lot of these soft robotic technologies and soft electronics to start making real world impact and everything from human motor assistance, through wearable devices and through these exoskeletons, all the way, as you can see in the bottom a few panels here, to different types of uses of soft robotics in industrial automation and robot grasping. I'll just kind of show a few highlight videos here. This is just using kind of the more traditional pneumatic actuators that have been around for a few decades now. I'll just kind of skip ahead here. But here it's kind of used for this precision stage. So these are the pneumatic actuators that are used to have this kind of force-controlled motion of these various end effectors that are used in automation. So this is, systems like this are being used today in industry. Something that's been growing and popularity lately have been these kind of soft robot end effectors. Instead of using those more traditional pneumatic actuators that I showed you in the last video, instead they have these kind of rubbery, kind of soft fingers that are used primarily to perform pick and place operations on very delicate objects. So you can imagine, like, baked goods and ripe fruits and things that would otherwise get crushed if you were to try to handle them using a parallel plate gripper. Here's, let me just kill the audio on this. This is from a company based out of Germany that's kind of really pushing the envelope in terms of integrating soft robotics and also stretchable electronics and sensors for creating these kind of bio-inspired robotic systems. And I'll kind of skip ahead here just so you can kind of see the robot at work. So again, by moving away from motors and conventional electronics, we can start engineering robotic systems that are quite compliant, soft, and lifelike. So I'll kind of, just in the interest of time, we have about a minute and a half left here. So I'll kind of gloss over these, but there's a lot of different market studies out there that predict quite a bit of growth within this field. A lot of that is going to be driven by the use of soft robotics within wearables. also in industrial automation, grippers. There's this other category here that actually relates to the use of soft robotics in medical applications. Pittsburgh, of course, you know, is a hotbed of kind of entrepreneurship and translation of a lot of robotics technologies. And I'll just kind of wrap up by just highlighting just some of the work out of my own group. These are just spin-offs that are all based here in Pittsburgh. These are all still fairly young companies, all in the pre-revenue stage. So in the sense that they get most of their funding either through VCs or through government funding agencies. But still, I mean, you know, initiatives that, even though they're still very early, you know, they're things that I'm really excited about and have given my former lab members an opportunity to find practical uses and impact for their work. So Life4 Labs is one, working on these sticker-like wearable electronics. REC is doing a lot of interesting work using the liquid metal that I mentioned before to tailor the thermal and electrical properties of soft materials. And then lastly, ESAT actuation, which is looking at exoskeletons and wearables and ways that we can make these to be more lightweight and high performing. And then you know, John mentioned new SCAFE, and you know, that's going to be a real game changer, I think, for a lot of the work that we do, not just in my lab, but across the university in this space of soft robotics. I mean, this is going to be a really beautiful space. Hopefully, a lot of you, you know, if, you know, will get a chance, you know, to visit soon. The new space when it's completed. Here's just a snapshot of what some of the shared resource lab spaces are going to look at. So, a really exciting opportunity to not just do a lot of the soft robotics kind of synthesis and characterization work, but also kind of work with folks within the MECI department and across the college on biohybrid systems, tissue engineering, you know, biochemistry, and then looking at these kind of, you know, more advanced kind of emerging types of applications. So I'll kind of leave it at that. I'm a little bit over 20 minutes. So a lot of great prospects and a lot of kind of, you know, open questions that remain for the field. So thank you so much.
Wow, Carmel, that I think I speak for all of us when I say that was a fascinating presentation, and thank you so much for presenting it. I learned a couple of things. I hope everybody else who's watching did as well. So now we turn to the Q&A part of the session, and we've already got a bunch of questions that have been submitted by our attendees. And just as a reminder to everyone who's online with us, if you do want to submit a question for Carmel, we will try to get to it today as if at all possible. You can submit a question by going to the bottom of your screen. Probably it's on the bottom of your screen. There's a little Q&A button, and just submitting a question through there. So Carmel, to get us started, you may have answered this, but we had a question about what applications do you think are closest to adoption or commercialization? And you mentioned some healthcare adoptions and applications. So where do you think that might land?
So I think healthcare represents is a really exciting opportunity. I mean, just a little bit of background, right? So the most successful kind of soft robotics company is called Soft Robotics Inc. And it builds, I showed a couple of their videos where they have these kind of soft robot grippers. One was like picking up Twinkies and off a conveyor belt, right? That company started out trying to be a healthcare company. So they thought that, oh, soft robotics, you know, the whole point was to make exoskeletons and assistive devices. So that's kind of where they focused, you know, their first year or two. And, you know, just because I was kind of, you know, working with a lot of the, you know, the researchers and folks kind of who were involved in the inception of that company, I learned that very quickly they had a pivot because yes, there's tremendous potential to use these robotic systems in healthcare, whether it's for assistive devices or for rehabilitation or for, you know, wearable health monitoring or for minimally invasive surgery. Those are all kind of amazing and great things. But in terms of just the acute needs right now, the pain points that are going to get, you know, companies to start implementing those technologies today, it wasn't how do you pick up a Twinkie and put it in a box, right? I mean, it's how do you handle fruit, you know, and so that was kind of one of the things. Yeah, not as glamorous, not as sexy as the healthcare, maybe not as lucrative kind of in the long term, but certainly in the short term, you know, it represents an important kind of beachhead for the field. And so that's kind of what kind of got things kind of launched. However, since then we have seen a lot of growth in companies that are adopting soft robotic technologies and architectures for exoskeletons. So I would say that kind of represents the other kind of big growth opportunity.
Excellent, thank you. And as we're thinking about these applications and commercializations, we had another question come in about how do the soft materials compare in cost to the quote unquote hard robotics, more traditional materials?
So they're actually commodity materials, so as cheap, if not cheaper, than what's currently used. One of the other motivations for this, and this is at least, this is actually predates my time even at CMU back when I was a postdoc, and the early discussions about soft robotics was actually, yes, I mean, it allows for new functionalities and more lifelike motion, but it also, in a sense, democratizes robotics by allowing you to build robots out of a much wider range of materials. It really expands the materials palette, including materials that are much cheaper and much more accessible to folks. So a lot of these systems are just, I mean, it's just rubber and air and, water or hydraulic fluid. Liquid metal is, a little bit pricier, right, per kilogram, say, than rubber, but still actually cheaper than a lot of the precious metals that are used in electronics, in the microelectronics industry. So no, I mean, it's as cheap, if not cheaper.
Good, thank you. And that, since we're talking about dollars and cents, we got a question that said, what would you talked a lot about sort of, funding from various agencies and so on. What would you or could you do if funding was not an issue?
If funding was not an issue, I think that the community should really focus on some of the grand challenges in the field that represent kind of scientific, fundamental kind of bottlenecks. That's the best use of funding for the academic community. Anything else, I mean, if the technology is somewhat more mature, if there's a kind of a good commercial case for it, there's a whole, ecosystem there that will kind of fund and support that and make that a reality. So I would say kind of the areas that kind of could use the most focus would be, again, medical robotics, especially kind of in the minimally invasive surgery space. That kind of represents one, but I would say probably bigger than that would be in using soft robotics for human motor assistance, rehabilitation. So imagine kind of exosuits, if you will. That's something where there's still a lot of challenges on the material side. There's a lot of challenges in terms of actually working with human subjects and doing those large, human subject studies. I mean, there's a wide spectrum there of things that just hasn't been done yet. And I would say that's probably where I'd focus the bulk of the funding. There's kind of more exotic stuff like the biohybrid systems, merging the tissue engineering with soft material systems. That's also something that, if the funding wasn't, an issue, we could focus on that. But I would say kind of the human motor assistance, that would really unlock really what motivated the field in the first place and unlock its full potential. That
would change so many lives, I think.
Right.
Great, thank you. Well, switching gears a little bit, talking about, we had a question come in about other people who have influenced your work. So let me just read this question as it came in. Can you comment on the impact of Rodney Brooks's original work at Heartland Robotics and MIT on soft robotics, such as Baxter? Has this work and his soft gripper research impacted your research and the industry writ large?
Yeah, it's had tremendous impact. I would say that Rodney Brooks, I mean, Heartland Robotics, Baxter, they're just kind of one of the many pioneers, I think, in terms of co-robotics and bringing robots out of the factories, out of the plants out from behind the cages and bringing them into these domestic settings. I think what kind of Baxter also kind of taught us is that you don't have to build the whole thing out of soft, squishy materials. I mean, there's a lot you can do just with kind of more conventional robotic hardware. And if you have good computer vision, if you have kind of good sensing, if you have enough kind of fail safes in there, you can engineer these systems actually to be quite compatible with the human body. Robots also are tremendous tools, within the academic community, and so. I think that kind of represents, the first of kind of many, efforts and attempts at bringing these robotic systems into our everyday lives. So, this kind of talk, it was a whirlwind overview. I just didn't have time to really credit a lot of the pioneers, in this field and really kind of properly acknowledge all the folks that have been deeply influential on me in terms of the work that I've done in soft robotics.
Yeah, I have a feeling we could talk hours about all this. It would be a lot of fun.
Yeah.
Another question about the company that you mentioned, LifeWare. What types of things can LifeWare track?
So they do physiological monitoring, so vitals monitoring, so heart rate, respiration rate, blood oxygenation, body motion, with IMUs, temperature. So basically, pretty much the standard. So like if you are in an emergency situation, or if you have a paramedic come, the types of things that that they would usually data that they would collect with one of those kind of bigger kind of suitcase size monitors, they can basically do it with these kind of sticker-like patches. Something they're currently working on, where they're making some good progress, and actually just launched some pretty extensive human subject studies, is on blood pressure monitoring using these stickers, and that would be a real game changer, I think, for emergency medicine and kind of or at home healthcare, or So the idea basically is to just kind of get rid of all those bulky kind of monitors and all those tethers and wires that you have to connect, and just replace everything with just a few stickers that are put in various parts of your body.
That's exciting. I can't wait till that happens.
Yeah, well, neither could when my wife was giving birth. Actually, we've had 2 kids now, and each time I'm just astounded by just how many wires and tethers she's kind of connected to monitor her health and the baby's health. And she would be the first. She's telling me she should be the first in line for just something that would just be a sticker that would replace all that.
It would simplify a lot of that.
Yep.
Okay, so for students, we haven't had a question like this, but for students who are interested in working on a soft robotics career, what are the types of subjects and skills do you think they should master to be successful in this field?
So I mentioned kind of before in one of the earlier questions, I mean, one of the motivations, or maybe I should say one of the reasons soft robotics has caught on is because it democratizes the field of robotics. So no longer is it just in the domain of mechanical engineering or just within computer science, but now it's something that people from all different backgrounds, all different levels of interest, different stages in their training can participate in. The types of material systems, whether it's kind of these balloon type robots, or the sticker-like soft electronics, or work with shape memory alloy or biohybrid systems. I mean, you can imagine this will, can also engage people within the design community. I mean, I've worked with, folks within architecture, right? So kind of similar to John, there's kind of a lot of different disciplines that can be, that can interface, with this field. In my research group alone, I mean, I've had folks from civil engineering background. My own training is actually civil engineering, funny enough, even though I'm in mechanical. My undergrad was in civil. So folks who kind of, are interested in mechanics and materials and structures. I've had chemists, biomedical engineers, material scientists, of course, a lot of folks from the Robotics Institute, folks within the HCI Institute. So there's kind of a lot of crossover. So whether you're more interested in kind of the algorithmic side of things, the software and the simulation, whether you want to do just more hands-on type of engineering, whether you want to do kind of more experimental kind of wet lab, laboratory chemistry type stuff, whether you want to do more design. I mean, there's kind of so many different directions from which you can enter the field of soft robotics, and so many unique ways you can contribute. So I would say almost, any kind of background I think is useful. But the important skills to have, of course, are to be able to work in teams, to have, obviously have that working familiarity with a lot of different disciplines. You can't be too siloed. And you also, whatever it is that you bring to the table, you have to have deep mastery of it, right? So you have to kind of excel at whatever it is that you're bringing in that's unique, and then have a working familiarity with other people's work, so that your kind of deep expertise can complement the expertise of other folks. And so, yeah, I would say pretty much anything, could potentially get you there.
Very good. Thank you.
Yep.
Another question's come in that's quite interesting. It's sort of a conjectural question. Could much of this work be done with hard materials that are paired with really good sensors and feedback and computation?
It could, and that's what's been done basically. I mean, the way that roboticists kind of achieve compliance and they achieve human compatibility is doing exactly that. So having just more articulation, more sensors, just faster feedback, having less lag, less latency. Those are all things that certainly can accomplish a lot of the same things. And I wouldn't say that soft robotics is inherently better than those approaches. I think that there's a lot of advantages to kind of the more computer or algorithmically driven types of approaches to kind of robotics and compliance and human compatibility. I would say that a lot of these technologies are complementary to that. Maybe the bulk of your robot has a lot of those features, but by having a few soft elements here and there, maybe that can kind of cut down on the number of cameras you need. Maybe it cuts down on the number of sensors. Maybe it cuts down, or maybe it gives you a little bit more leeway, so you can have a little bit of latency, or you don't need as much performance in your sensors, your actuators, or your signal processing. And at the end of the day, that just translates into a higher performing, cheaper, more lightweight system.
Good. Thank you for that. On the flip side, sort of if we flip that question a little bit, what do you think are the main limitations of soft robotics?
So the practical limitation is soft and squishy materials aren't very load bearing. So that very first video I showed of all those robot arms in an industrial plant manufacturing those cars, you're not really going to do that with kind of soft robotics. And how kind of that applies to so many other domains of engineering, right? I mean, you're not going to build an aircraft carrier by mimicking the soft body of an octopus, so the soft robotic systems, they're not going to be great for kind of heavy duty load bearing type applications. I would say kind of some of the other limitations are that there isn't a perfect replacement for the motors. I mean, any of those actuators that I showed you, those quote artificial muscles, have their kind of practical limitations in terms of poor energy efficiency, or not just having enough kind of power or work density. Also on the computing side, I mean, yes, there's a lot we can do with making stretchable circuitry, but when it comes to computing chips, I mean, there's no replacement for for silicon, right? And just kind of your kind of conventional field effect transistors. I mean, you're not going to find any analogy to that in kind of soft robotics. I mean, in nature you can find analogies, in nervous tissue, right? But we're far off from replicating that in an engineered system.
Yeah, thank you. At one point in your presentation, you referenced that there is a German company that's doing some of this work. What is the name of that company?
The name of that company is Festo, F-E-S-T-O. And they've really been a pioneer. I mean, pioneering the use of these pneumatic actuators in industrial automation. They have a lot. I showed that one video of that soft bionic hand. I mean, they have kind of a lot of these demos. I mean, these are kind of analogous to the Honda Asimov robot, right? These are more for show, but what they actually make their money off of are just kind of the standard pneumatic actuators for industry.
Good, thank you. What do you think is the next breakthrough in soft robotics? Is it material identification, control, computation, structure modeling, something else?
I think that the next breakthrough, one of the next big needs that a lot of my colleagues are working on, and something that I've been trying to get involved with as well, is actually more on bridging that gap between basically the materials and hardware and architectures and soft robotics with the algorithmic frameworks that are used in conventional robotics. And so, the robotic operating system, ROS, is of course one, that's commonly used kind of within more conventional robotics. But along with that are all sorts of different types of, more standardized controllers and simulation tools, physics engines, methods in AI, data-driven techniques, ways that, robots learn. And right now, I would say kind of the big challenge is in applying a lot of those to soft robotic systems so that roboticists kind of who are working in practice can actually start using some of these material systems. Right now, there's kind of this divide. It's like, this motley crew of, designers and engineers and computer scientists and chemists and, all sorts of folks, working in the soft robotics space, but they're not necessarily designing systems that can be easily incorporated into the framework of kind of more conventional kind of robotics practice. And so I would say that, and one of the big, points are kind of the controls and simulation tools that are being developed for soft robotics that will help bridge that gap.
Great, thank you. We have time for just a couple more questions, and I'll just take a breath here to remind everybody that we will be sending out a recording of this Faculty Insights presentation so that you can view it again and maybe catch some things that you might have missed the first time around, share it with your friends and so on. So we'll be sending that out hopefully before the end of the calendar year. We'll be able to get this out to you, but let's take maybe one more question. I'm just double checking here. Okay. So you mentioned that some of the soft robotics work that you're doing sort of mimics a brittle star and some other biological organisms. Can we, in reverse, learn about biological systems through these soft robotics mimics?
Oh, definitely. And in fact, I'll go a step further. Right now, we have a project with Phil Duke. He's another professor within the Becky department. And hopefully I'm not giving too much away just because we haven't submitted the paper yet. We're just finishing up the writing. But we're actually using soft robotics to resurrect the ancient, long extinct ancestor to the brittle star that lived, I think, about like 400, 500 million years ago. So there we're using soft robotics basically to design robots based on the fossil record to have an understanding of what these robots might have, behaved like, how they would have moved, how do they navigate, the prehistoric, kind of environments that they were in. Because we don't have, not only do we not have, really much understanding of those organisms and their mechanics, but we don't have any kind of modern day analogy either that we can point to. We just have the fossil record and that's it. And then all the species since that evolved from that look nothing like, what existed then. So yes, there's a tremendous amount that we can learn, not just about organisms today and how they move, their different locomotion gates and how they navigate different terrains and environments, but also there's a lot we can learn about extinct organisms as well.
That's fascinating. Fascinating. I'm glad that question was asked. All right. I said we had time for one more, but I want to end with we just got a great one. I want to end with a big question. So you discussed some exciting work in combining soft robotics with tissue engineering to create biohybrid robots. If a machine is made out of living materials and has intelligence, do you think it's alive? And are there any ethical or regulatory concerns when we start building robots out of living tissue?
It's alive. I mean, as far as I'm concerned, I mean, I think even the robots without the biohybrid, I mean, they kind of seem alive to me. I mean, but yeah, there are certainly, I mean, there's the practical concerns, of course, with any kind of tissue engineering and the biosafety types of constraints that have to be placed. From an ethical standpoint, I mean, there's that's kind of way over my head, in terms of how you get this through IRB. I mean, usually the ethical concern, which is a very real one, is that a lot of those the tissue, it might be harvested actually, from organisms. In some cases, it might actually be surgically removed from living organisms, and I think that would be probably the biggest ethical question, right? So this actually dates back like 100 years. Folks would dissect frogs and they would use frog muscle and power robots, right? I mean, we have Vicky Wexler Wood here, who's done really kind of phenomenal work in terms of studying sea slugs and actually kind of extracting kind of the muscle tissue from sea slugs and exploring, not just characterizing it, but also exploring the use of that in soft and biohybrid robotic systems. So I would say that probably represents the first question. But then when you start assembling these, then you do kind of cross over. At what point, is it a robotic system? And at what point is it a natural living organism that you just augmented with kind of soft robotics? I mean, and I guess that would be considered a cyborg, at that point. And certainly when you kind of cross that line, yes, those are kind of questions where and they have been explored already. I mean, there's a precedent for really kind of understanding what is ethical versus not with those systems.
Thank you. That's a heavy question.
Yeah. And and I will say, I mean, to folks who were excited by what they saw in the talk, and maybe some of the videos or some of the content, I kind of went through this quickly, and maybe even when you see the recording, maybe if you don't catch anything, feel free to reach out to me. I mean, I'm not hard to find. Just send me an email. I'd be happy to kind of send you content based on what you saw.
Well, thank you so much, Carmel. This was a fascinating hour to spend with you. So I'm so glad that you were able to share this with us today and with all of our attendees. And I want to thank everyone who joined us today online to hear about Carmel's work. Really appreciate your participation in this. Again, look for the recording to come out soon. And then we'll be doing another one of these faculty insights. So please watch your email for another invitation to our next one in the new year. And as we close out 2022, I hope you all have a lovely holiday season and a happy new year, and we'll see you in the new year.